In the next few examples, we will look at some of the applications of exponential functions in the real world. One of these applications is calculating interest, which is a very common application in financial situations. The amount of money A that a principal P will grow to after T years at an interest rate R, written in decimal form, compounded N times per year, is given by the following formula. Suppose that $1,000 is deposited in an account paying 4% interest per year, compounded quarterly, so that's 4 times per year. We're asked to find the amount that will be in the account after 10 years when there have been no withdrawals. So the first thing we need to do is identify what P, R, N, and T all stand for. So first we have that P is equal to 1,000 because that was the original deposited amount. That is the principal. We see that there is an interest rate of 4%, which we will write as 0.04 in its decimal form. Because the interest is compounded quarterly, 4 times per year, N will equal 4. And we are letting the money grow over 10 years, so T will equal 10. So substituting all of these values into the formula above, we have that A is equal to 1,000 times 1 plus 0.04 over 4 to the power 4 times 10. A good scientific calculator will allow you to enter this quantity exactly as you see it here, but you may want to simplify it just a tad to make it easier. Inside the parentheses, 0.04 divided by 4 is 0.01. So when added to 1, that just becomes 1.01. 4 times 10 on the exponent is 40. So it may be much easier for you to enter this on your calculator. I've already done this on my calculator, and I have found that the total amount in the account after 10 years is $1,488.86. The next question is, how much interest is earned over the 10-year period? Well, our original deposit amount was $1,000. So if we just do a simple subtraction here, the new amount minus the starting amount will give us how much it grew by, which is $488.86. That's a good amount of interest. The next application of exponential functions has to do with growth. Not necessarily financially, we see this more in science applications. For example, a model that describes the population P after a certain time T is given by the following equation. P of T is equal to P naught, so that 0 is a subscript, times E raised to the K times T power. Here, P naught is the initial population, the starting population. K is called our relative growth rate, and it must be a positive number. Let's use this formula to answer the following example. The population of a rural city follows the exponential growth model. P of T is equal to 2,300 times E to the 0.041 times T power, where T is the number of years after 1985. I'm going to underline that because that's going to be super important. T counts the number of years since the year 1985. So the first question is, what was the population of the city in 1985? So in other words, what was the initial population? Well, if we compare the formula given to the generic formula above, we see that P naught is equal to 2,300. This is the initial population in the first year which is 1985. Second question, what is the relative growth rate as a percentage? So in other words, what is K? We see here that K is equal to 0.041. Written as a percentage, this is 4.1%. To get from decimal to a percentage, you simply multiply by 100%, which is going to move that decimal place 2 spaces to the right. And the next question is, use this model to approximate the population in the year 2032. So we have to calculate T, which is the number of years since 1985. So T will equal 2032 minus 1985. So we see that this is 47 years. So we'll have A equals 2300 times E to the power 0.041 times 47. Again, using a good scientific calculator to enter this carefully, we'll find that the population has grown significantly to 15,798 approximately. We do have a small decimal after the decimal point, but we can either round down or up in this case. Finally, we have an application back to financials for continuously compounded interest. The formula that we saw previously was for compounding interest a fixed number of times per year, so n times per year. But what if n was allowed to grow without bound? So we're compounding not quarterly, not monthly, not weekly, not daily, not even every minute, but just continuously. The growth will be much more quickly. And as n increases, so let me write that original equation here from above. So if we take this formula and allow n to grow without bound, then we get this formula, where A is equal to P times E to the RT power. The question here is, how much money would be in an account after 5 years if an original investment of $6,000 was compounded continuously at 4.5% interest? So here we have that the original amount is $6,000. We have that the interest rate is 4.5%, which we'll write as 0.045 in decimal form. And we have here that we are allowing 5 years to go by. So in this case, we have A equals P times E to the R times T power. Entering this carefully into a scientific calculator will tell us that after 5 years, the $6,000 will grow to $7,513.94.